Hi, I'm Csongor Tamas. I'm a student at Budapest University of Technology and Economics and a member of Crisis Lab. And for this research, my supervisors were Dr. Boldizsár Bencsát and Levente Buttyán. All right, so let's start with a problem statement. We needed fresh ransomwares for research purposes as Crisis Lab. And we defined fresh as from the last week, from campaigns from the last week or month. And my task was to deliver this. So how do I do it? First, I looked at the news and found that, all right, Maersk was hit by NotPetya ransomware. And I thought that, damn, those guys have the freshest ransomwares. And yes, and I don't, so how lucky they are. Yeah, so here is a solution for getting fresh ransomwares. But unfortunately, I was unable to build a $21 billion shipping company during a semester, so I had to look for other solutions. And my concept was the following. What if we had a collection of old ransomwares and a feed of new files from an outsource? And the method that combined these and the output would be fresh ransomwares. All right, but we can generalize this. Not for ransomwares, but what if we change the input, the old ransomware corpus input, to a search corpus? Then the output would be similar samples to the search corpus. All right, this might be familiar to you as VirusTotal hunting. They use Yara rules, and the method is Yara rule matching. And yeah, it is quite expensive, but okay. The problem with this is that Yara rules, although they can be automatically generated, they do not work that well, and they need a collection of very similar files to deliver more effective rules. And the process of Yara rule matching is fairly slow, so it's on the scale of 0.01 seconds, and this is on a fairly simple rule on a fairly small file. And I needed a much faster method. So back to my work. We need three things: old ransomwares, feed of new files, and the method. Now, the feed of new files were provided to me by Locality Technologies. These feed of new files came in every day. They were all malware, and a database was also accessible to me of roughly 300 million live malware samples. All right, so we have one of the three things I need. Next up is the old ransomware corpus. I collected it through a course of 2 or 3 months, looking at the news for campaigns, downloading the hashes from the samples for the hashes from VirusTotal. So this took a while. And now for the method. Of course, you could guess it was LSH, locality sensitive hashing. Now, what is locality sensitive hashing? The basic concept of it is the following. For similar data, it generates similar hash. That's the main concept. It aims to maximize the probability of a collision for similar items. So similar items are going to equal for similar hash. This similarity between the digest, the hashes, is not surely visible to our eyes, but a distance calculating algorithm is also provided with the locality sensitive hashing method that outputs a number, roughly a score or a distance, that displays the similarity between the two source files. Let's look at some examples. So first up, I'm going to talk about SSDeep, because this is the only locality sensitive hashing method that is available in public malware databases, like in VirusTotal. Yeah, and it uses an algorithm called context-triggered piecewise hashing. It depends on the time if I'm going to explain what it means. Yeah. The next one I looked at is SDHash. It uses statistically improbable features. The idea behind this is the following. if an improbable feature is present in a group of files in every sample, then if a new sample comes up and this improbable feature is present in that file, then it is almost, so the probability of this file not belonging to the group is fairly low. And I'm not going to describe SD hash in the followings, because the test showed that SD hash was not applicable for malware classification. And the third one I looked at is TLSH, that stands for Trend Micro Locality Sensitive Hash. This algorithm looks at the input byte stream in 5 grams with a sliding window, creates statistics of these 5 grams, and basically the hash stores these statistics. Okay, so let's look at an example. There are you can see two texts and the hashes for them. The top and the bottom texts only differ in the highlighted character. And as we can see, the digest, the similarity between the digest is even visible to our naked eyes. For TLSH, it is not this straightforward, so equal characters. Yeah. The reasons why I chose locality sensitive hashing are the following. First, the small data to store. So for error rule matching, we need the whole binary. The process of error rule matching needs to go through the whole binary and get a rule and look at matching, while SSDeep and TLSH, we only need to store roughly 100 bytes. And this is good, because for 300 million malwares, this is only going to equal about 30 gigabytes of data. Yeah. The second reason is fast automatic generation. SSDeep and TLSH both generate digest in the scale of 0.1 or 0.01 seconds. And last, fast comparison time. So for as I mentioned, a fairly easy error rule and a fairly small file, 0.01 seconds took the process of your rule matching took. Yeah. And as for SSDeep and TLSH, it is on the scale of 1 millisecond, which is like 10 times or even 100 times faster. And this does not matter on the file size, because the hash size is roughly always the same. So for TLSH, it is always 70 bytes. So it won't change. All right, we've seen the pros for locality sensitive hashing, but are they applicable for our task? I took one daily feed from this database. It contained about roughly 35,000 real malware binaries. But they were not labeled, they were not classified, so the evaluation would be difficult. Now, first up, I calculated the SD hash and TLSH, no, the SSDeep and TLSH digest for every sample, and then the cross-references between every other sample. So in the following, I worked with, I gained a database of distances, and I implemented 3 clustering algorithms to evaluate the usability of locality sensitive hash, these 2 locality sensitive hashing methods. I'm not going to describe them because, yeah, so all right, I'm going to mention the third one because that was the most effective. If there were some groups already created and a new file came up and new digest was generated, then this file was inserted in this group if it was close to at least a few members of the group. So one closeness to a sample is not enough, as I found out, because then one gigantic group was created with like 20,000 files and like another 20,000 groups with only one sample in them. Yeah, as for the results, as I mentioned, I evaluated by hand, so I obtained groups from these 3 clustering algorithms, and I downloaded the binaries and looked at them by them, the disassembly, yeah, and hybrid analysis. and it showed that samples in the same group are similar. So this process of locality sensitive hatching works. And I have to mention that so these groups contained more than one samples, because of course if a group contains one sample, it is similar to itself. So there were groups created, and the files in them were similar to each other. Now, as I mentioned, SD-Has was not applicable, so it was like totally wrong. Another thing I found was that SSDeep score was badly scaled. So the distance calculation in SSDeep, the output was a score between 0 to 100, where 0 equal to a mismatch and 100 equal to a perfect match. Now I found that the score of 1, if a distance was 1, then we could be like 70% sure that this similarity was correct. So we do not have the range to define the threshold between 0 and 100, because the score of 1 means similarity in most cases. Yeah, and there were similar samples in different groups. So and the next one is that TLSH appeared to be the best. Yeah, because the threshold, I selected the thresholds to obtain no false positives. So like the 70 threshold and the threshold of 1 were selected through this measure. And with these thresholds, there were similar samples in different groups. But this is not a problem for us, because we only wanted to find similar samples. We did not aim to find every similar sample in a database. All right, so let's look at some hashes. First, this search was completed by both SSDeep and TLSH. This was on the whole database, so not on this small corpus. And so now we see the SSDeep results. The original sample I searched for was this Grand Crab sample. You can see the SSDeep hash for it. And the algorithm found the similar samples on the bottom. And as we can see, there are similar characters in the hashes. They are displayed in the red boxes. And of course, these files are not the same, so there are different characters as well. So for the same search, the input is the same sample, but now it's the TLSH digest value. And the algorithm was unable to find the similar samples. So the hashes you can see on the bottom are the TLSH hashes for the similar samples that were found by SSDeep. And as we can see that there are similar characters in these two digests, but with the threshold of 70, the algorithm deemed the bottom samples different from the one on top. All right, so yeah, and next up is the other way around. So the same search, I took the same search with a Saturn ransomware one sample as an input. And now it was TLSH that found the similar samples. You can see you are further away, but you can see that the digests are visible. The similarity is visible between them. And this time it was SSDeep that was unable to find the similarity, although for the similar finds that were found by TLSH, the similarity is visible even through SSDeep hashes. But from the original sample, it was not. So then I moved on to the real database. As I mentioned, it contained 300 million Malware samples. The hash generation for SSDeep and TLSH took roughly the summer, so 2 months. And but then so in the previous, so for the small data set, I calculated cross-references between every 2 samples. Now, this does not scale well. So for 300 million samples, it would roughly take 3 million years. But we do not aim to group the whole, to clusterize the whole 300 million malware database. We only need to search for a small corpus. And that way, we only need to calculate the cross-reference between every member of the corpus and the 300 million malwares in the database. So the ransomware corpus I collected through the months now contains 477 samples from 15 different families, ransomware families. And my implementation currently uses one process only on one thread. And for a search for one sample, so if the inputs corpus only contains one sample, then SSDeep search is completed in roughly 10 or 20 minutes for 300 million files. And for TLSH, it's roughly 50 minutes. I think that's incredible. And for all the 477 samples, it took like 2 days for both of the hashes to complete. Yeah, so it is live and working. So what I completed was I had a malware database, I selected a search corpus, and through the method and implementation of TLSH, I was able to find similar samples from this malware database. And here's the same with the first task, so first problem. Yeah, future work. As you could see, I only used one process on one thread. Now, parallelization could result in much better, could provide much better results, like from, yeah, you know what I mean. I will widen this ransomware corpus to obtain maybe 20 or more families and more samples. Now, I looked at the source code of both SDHash and TLSH, and I found that we could develop a better LSH method. So both of these locality sensitive hashes can be easily fooled if that was the intent of the APTs. But we could develop better TLS or LSH methods. That was what I found, and yeah, it's a future work. And of course, there is a chance for labeling this 300 million malware database, but not by comparing every 2 samples, but by grouping them in small groups and only calculating new samples distance from 1 or 2 or a few members of the group. All right, so that was my work and presentation. Thank you for your attention, and if you have any questions, I'm here. Thank you.